point in the future. So in order to avoid that strong reliance on technology in the future, we need to reduce emissions steeply up to 2030 and really stick to those emissions budgets. And just to briefly give a little overview of the emissions budget. So the IPCC calculated in 2018 what the global CO2 budget would be to give us a 66% chance of staying below or at 1.5 degrees. So this was 420 gigatons of CO2. So if we take off what we've actually emitted since then, this brings us around 335 gigatons. So this is equal to less than 10 years of current emissions for the entire 1.5 degrees budget. And something that's really important to this, to the context of this talk, is that in addition to sticking to this budget, which requires deep and rapid reductions of emissions on the ground, we also have to remove massive amounts of emissions that are already in the atmosphere. So this requires large areas of land to do that, whichever method we really look at. And just to briefly talk through some of those methods for actually taking emissions from the atmosphere. So this is essential to do for the 1.5 degrees goal and most likely needed for 2 degrees as well. Like I said, all of these methods require large areas of land. So we have some of the high-tech options such as bioenergy, carbon capture and storage. So we're basically growing biofuels such as miscanthus, transferring them to power stations, burning them and capturing the gases before they're released to the atmosphere, scrubbing out the CO2 and burying that underground in some disused geological formations. As you can imagine, this technology doesn't exist right now at the scale that it's needed and may never exist. So this is a major risk. And what's probably even more alarming is that many climate change mitigation plans really heavily rely on this technology in the future to actually achieve those emissions reductions. So this is microbes in the soil or biochar in the soil. And really the only option that we actually have right now at the scale needed is as simple as regrowing vegetation. So things such as reforestation, for example. Of course, this also requires large areas of land to do that. So we need to look at what land we could actually use in order to reforest on the scale needed to actually achieve those carbon sequestration goals. So agriculture is the biggest land user globally right now. Animal agriculture specifically uses the bulk of that land, so 83% of the agricultural land. And if we look at the sort of efficiency of that use, it's actually very low. So in exchange for 83% of our agricultural land, animal agriculture delivers 8% of calories and 37% of protein for global consumption. Conversely, crops use 17% of agricultural land and provide 82% of calories and 63% of protein for global consumption. So food production is also a major contributor to past deforestation. So it's a direct driver around 80% worldwide. Again, animal agriculture has a disproportionate impact here and is responsible for around 65% of all land use change since 1960. And is also linked to around 80% of deforestation in the Brazilian Amazon. Of course, forests are a really important natural carbon sink. And as I said, that's really all we have right now. We don't have any sort of artificial means of capturing and storing carbon, so we really need these natural sinks. And they're also really important areas for biodiversity as well, which is a separate issue, but also very related in that it basically helps to provide a functioning ecosystem, which is really essential. So we have this sort of legacy of animal agriculture being a major contributor to the loss of carbon sinks, as well as still occupying the bulk of that agricultural land. So in addition to the demand for animal products increasing, really why they actually use all of that land is because they're so inefficient to produce. So for example, to produce 1 calorie of beef actually requires 37 calories of plants to produce, pork requires 12 calories, chicken requires 9, and eggs and dairy each require 6 calories. Globally, a third of all crop calories are fed to farmed animals, and only around 12% of those calories come back as human edible food. So we're losing over a third of all calories produced before it gets to anybody's plate. So this is a major source of food waste that we don't currently account for in the same way that we look at, say, post-consumer food waste. So it's really much more efficient for us to just eat plants directly. An example of this is a study published in 2018. So they looked at the US, which currently uses 67% of all calories produced for livestock feed. And what they found is that by reconfiguring that crop production and instead growing foods that optimize for human health and least resources, they could actually feed twice as many people from that same area of land. We also need to look at, well, what if we don't do anything about agricultural emissions? Is that an option? So one example is from an article I published in 2018. And what I found is that if we don't take any action on livestock and it continues under business as usual, by 2030, it would actually use around half of the budget for the 1.5 degrees goal and around 37% of the budget for the 2 degrees goal. So this is by 2030. So we can reduce livestock emissions to an extent through technological measures, but the actual benefits, somewhere around 10% reduction is the latest estimate, is just really not enough it's really not going to get us the reductions that we need from that sector, basically. So reducing the consumption of animal products is absolutely unavoidable. And if we don't do that, it basically requires other sectors to massively increase their mitigation efforts beyond anything which is planned or realistic. So we need radical action far beyond anything that's currently planned across all sectors, including agriculture. So I think it's really important to stress here that what I'm talking about and the results that I'm going to show are not a standalone measure. So we still need every other sector to do everything that they can as well. So in our analysis, we focus on the carbon dioxide removal potential of returning some of the land use for animal agriculture back to its native vegetation cover. So in this case, that was either forest or grassland. Again, we focus on animal agriculture because of its current large land occupation, its large historical contribution to the loss of natural carbon sinks, and its low food output to land use ratio. So this is really a kind of obvious first port of call to look at in terms of these shifts. And so this is an article that we published in at the end of September. And this is basically what I'm going to just briefly run through now. So we posed 3 main research questions. So first of all, we wanted to know how much agricultural land could be restored to native vegetation cover. And in doing that, how much carbon could we actually remove from the atmosphere? And what impact might these shifts have on food production? And it's worth pointing out, if it wasn't obvious already, that we're really modeling deep transformations to agriculture here, and we're really not considering business as usual or attempting to maintain business as usual in any way. So our scenarios, first of all, we returned permanent pasture and animal feed cropland to forest. So this really gives us the current carbon opportunity cost of animal agriculture. So as I said, agriculture on deforested land and continuing to be on deforested land is basically preventing that vegetation from restoring. Therefore, there's an opportunity cost there in terms of the carbon sequestration potential. So that was our first step to actually look at that opportunity costs. And secondly, we looked at 3 different dietary scenarios and the carbon dioxide removal potential of each of those 3 scenarios. So we looked at a business as usual, we looked at an eat land sit, and we looked at a vegan diet. So just to briefly run through the methodology. So there were 4 main points. So the first 2 were really to map out globally. So we did a spatial mapping exercise of where all of the crops were currently distributed. So this was for 175 crops. And we basically used existing data sets from the literature and just sort of mapped them in new ways in order to do this analysis. So we took the FAO's definition of permanent pasture land. So this is any land used for grazing for 5 years for more than 100 days per year. So this is not going to include all land that's currently used for animal grazing. And we did this at a resolution of around 9 by 5 kilometers, sorry. So then we mapped out where the crops are being grown for direct human consumption versus animal feed crops, again using existing data sets from the literature. And then we mapped the carbon content of vegetation. So again, using existing data sets. So we had 6 global data sets for the carbon that would basically naturally occur if that land use was abandoned. So if we abandoned animal farming on that pasture land, then this is basically the carbon that would occur in that situation. So the average time frame that we assumed was around 30 years to actually achieve the maximum carbon sequestration potential. And it's worth pointing out that we measured the carbon existing already in pasture and cropland. So what we present is actually additional to what is already there in that land. So for the dietary scenarios, we looked at 3 scenarios. So again, we used existing data, the business as usual. We mapped the cropland expansion per continent and the pasture expansion of 6% from the literature by 2050. For the Eat Lancet diet, again, we used the recent guidelines from the published literature and the feed crops and pasture land using crop and forage estimates. Sorry. So just had a slight technical issue. In the vegan diet, in this scenario, we have all of the permanent pasture land taken out of production, plus the feed croplands, minus the cropland that would actually be needed to provide the macronutrients to replace those animal source foods. So this actually also factors in waste, so around 25% losses and waste, and also takes into account the variation in nutritional requirements among different demographics and for disparities in food availability. So we're basically not just modeling one kind of standard vegan diet and assuming that everyone in the world will be able to grow and consume that. So it's actually quite specific to those requirements. So this is a map of the carbon opportunity cost. So this is basically showing the density of vegetation. So this green chart here, the darkest green is the most dense carbon sequestration. So those dark green bits are where we would expect to see the most carbon sequestration. And this is on all land currently occupied, well, all permanent pasture land and all feed crop land. And essentially what we found is the carbon opportunity cost of that is around 153 gigatons of carbon. So around 72% of this amount comes from pasture land and around 28% of that carbon would be sequestered on disused feed crop land. So it's worth pointing out here that we didn't actually include emission savings of methane or nitrous oxide. So we're mainly just focusing, or we're only focusing on carbon in our analysis, but obviously those would be additional benefits as well. And they have already been quantified elsewhere, such as the Eat Lancet analysis. So we also looked at the what this looks like by region. So we basically split that out into these 4 different country income types. And we found that 70% of that sequestration potential that you could see on that map actually occurs in the high and upper middle income countries. So if we think back to the beginning where we could see the G20 emit around 78% of CO2, I think there's quite a strong link in there in terms of the high and upper middle income countries really taking a lead on these sorts of measures. And our results certainly indicate that there is a massive potential there for them to do that. So this is roughly split between cropland and pasture land in high income countries. So these boxes here. And around 70% from rewilding pasture land in upper middle income countries. So we also looked at the 3 dietary scenarios. And you can see here the business as usual. So this is basically if we carry on as usual up to 2050, feeding around 10 billion, we would actually need to expand cropland. And this was actually using optimistic yield assumptions for crops. And we still have to expand cropland and actually increase the greenhouse gas or carbon opportunity costs of agriculture going forward. Under the Eat Lancet diet, we could sequester around 332 gigatons of CO2, which is equivalent to around 9 years of current fossil fuel emissions. And under the vegan diet, where we have no animal source products, we sequester the most, and that would be around 547 gigatons of CO2. And just in case anybody doesn't know, the Eat Lancet diet is around 70% meat reduction compared to business as usual scenario. So how does this relate? As I said, the Lancet is equivalent to around 9 years of fossil fuel emissions and equal to around CO2 budget. The vegan diet extends this to 16 years and is equal to around 163% of the remaining CO2 budget. I don't think we should actually see this as kind of offsetting the need for action in other areas. So we shouldn't really consider it as extending the budget. It's just sort of an equivalent to give you an idea of what that actually means. And overall, this would actually make agriculture a net negative sector where it's currently a net positive emitter. So we also did this analysis for the UK. So I'll just briefly run through, or a similar analysis for the UK using the exact same method. So we actually published this ahead of the journal article. And this analysis, we looked at returning permanent pasture and animal feed croplands to forest. So this would be temperate forest in the UK. So this scenario maximizes the carbon dioxide removal, but might not meet micronutrient needs because we are using some of that cropland. So in the second scenario, we just looked at returning permanent pasture land to forest. So what we found is that the UK has currently around 40% of all land in the UK is used for animal agriculture, and 55% of all our cropland in the UK is used for animal feed. So this is what that looks like spatially. So at the top here, again, the darkest colouring is the greatest density of pasture land in this case. So we can see how that is spread spatially throughout the UK. And then down here we have all of the cropland. So it's roughly a sort of east-west split going on. And 55% of all this cropland is used for animal feed currently. In England, that's 56%. In Scotland, it's 49%. Wales, it's 49%. And in Northern Ireland, 58% of their cropland is used for animal feed crops. So in the first scenario, this would be the remaining, the cropland currently used for feed crops that would actually be returned to forest. And in this is the cropland that would be kept under food crops, and that alone would actually would provide enough calories and protein for the UK population. We didn't actually look at micronutrient needs, so we can't say anything about whether it would be sufficient in that regard. So in this scenario, this is what that would look like, especially again with the darkest green representing the densest, the most dense sequestration or the most vegetation cover. And that would remove around 4.4 billion tons of CO2 from the atmosphere under that scenario over the 30-year period. So most of this, around 73% of that amount, would actually come from restoring or reforesting pasture land, and around 27% from reforesting cropland. So the second scenario, where we just reforest the pasture land, we would have all of this cropland here remaining for human edible crop production. So it does look a little bit washed out on this graphic. So I just wanted to assure you that there was plenty of cropland in all of these other countries, and we're not just growing the crops in England. So this scenario of reforesting permanent pasture land in the UK would remove around 3.2 billion tons of CO2 from the atmosphere. And around 43% of that sequestration would occur from lands reforested in England, 32% in Scotland, 15% in Wales, and 10% in Northern Ireland. So how does this relate to UK climate goals? So in our first scenario, where we reforest permanent pasture and cropland, that would remove the equivalent of around 12 years of UK CO2 emissions and would essentially double the 1.5 degree budget up to 2050, and would also meet the shortfall in relation to the zero emissions target. More than meet the shortfall, sorry. So in our second scenario, where we have permanent pasture returned back to forest, this would remove the equivalent of around 9 years of UK CO2 emissions from the atmosphere up to 2050, up to 2050, or a 30-year time frame, would increase the 1.5 degree budget by around 75%, and would meet the bulk of the zero emissions shortfall. And again, these scenarios would actually make UK agriculture a net negative emitter from its current net positive state. So there are a whole range of different potential co-benefits from these scenarios. So basically, if we shift some of that feed cropland to human edible crops, we could help address the really low consumption of fruits and vegetables in the UK and high consumption of red and processed meats, which is a leading mortality risk factor in the UK. It could also help to meet increasing demand for plant-based foods and provide new opportunities for producers and farmers. There's a whole range of environmental benefits as well. As I said, we didn't actually measure the non-CO2 methane and nitrous oxide, but that would definitely be a major benefit of such a shift. We'd also expect to see a reduction in nutrient pollution. So for example, in the UK, pastures are the biggest user of nitrogen application. So we definitely expect to see a reduction in terms of nutrient pollution. We would also expect to see catchment areas restored to the extent that the forest would actually act as a flood defense again and filter water out to actually prevent flooding further downstream, or at least reduce that level of flooding. And obviously we have potentially lots of new habitat for wildlife restorations and reintroductions. So in the UK, we have a major biodiversity issue. So 15% are currently threatened with extinction. We already have 133 that are extinct, and agriculture has had the single largest impact in recent decades. And that's actually true globally as well. So this isn't just specific to the UK. What is specific to the UK is that it has a really low level of forest cover already. So any kind of movement towards these sort of reforestation scenarios would be very positive in that respect as well. And we also have new opportunities for landowners and recreation opportunities for the public. So I think this aspect is actually not something that we really talk about that much when we think about these kind of shifts, but I think it's really important when we think about the sort of well-being benefits that could actually arise from having much greater access to nature. So these are really quite significant benefits that are being quantified in the literature. So we definitely need to bear these sort of impacts in mind. So I think another really interesting aspect of these sort of shifts as well is to try and imagine what this would actually look like on the ground. So we have the numbers and we can put them into the context of CO2 budgets and how that would help by 2050 and so on, but what would it actually be like to experience? And I don't have an example from the UK, but I do have one from Oregon State. So this is Hart Mountain in Oregon State, where they essentially did rewilding just by removing cattle from the ground. So I'm just going to play this 2-minute video clip just to give a glimpse of this kind of transformation that we're talking about.
The only thing the managers did was remove the cattle. And then we just stand back and watch what happens. Aspen and willows are streamside biodiversity indicators. These woody plants connect with the birds. You can hear the understory shrubs and flowers. It's just incredible to see this. When the cattle were here in these meadows, the aspen would stay. They would be eating the small branches and the leaves. All the cattle were removed in 1990, and then we got this incredible flush of aspen here. So we have these young ones that are less than 25 years old, and then in contrast, we have these very large old ones that are just on their way out. This is about a 70-centimeter diameter aspen tree. Originated in the 1800s, before livestock arrived on Hart Mountain. This one here is 2.2 centimeters diameter. This came in about 10 years ago. We've taken some photographs since the cows have come off and compared those to what the willow looked like with the cows on the refuge. And it's just night and day. Just an incredible flush of willow and aspen all through this streamside area. It's quite a spectacle to see how nature can recover if it's just left on its own, how it can restore itself.
So of course those fauna and flora were very specific to that case study, but I think it's useful to just demonstrate and to bear that in mind what we're actually talking about. So of course we need to talk about the urgency of the situation and what solutions are needed, but I think we also need to really start sharing this vision of what that kind of future experience could be. So just to wrap up, so we've seen in the presentation that animal agriculture is a leading cause of land use change and is still a major land user in exchange for relatively little contribution to global nutrition. Repurposing animal agriculture land to forest or grassland makes a substantial contribution to climate goals and creating a Paris-compliant food system. And these are needed in addition to strong and rapid reductions in the short term. So as I said earlier, we can't just basically rely on any one sector to achieve all of the reductions needed. This is across sector, everything has to change. And the shift offers multiple co-benefits to climate ecosystems and human health. So repurposing agricultural land in this way must be undertaken immediately in order to reduce the risk of these tipping points that we looked at early on, and also to avoid the reliance on other kind of currently unproven technologies that may never actually exist in the future to actually remove emissions in the future. So it really is a way for us to reduce the risk early on as well. And I think what our research shows is that animal agriculture is certainly not just a methane issue. And I think that's really precluded it to some extent from being sort of a focus of climate discussions if we just think of it as a methane or nitrous oxide issue, because of course the current discussions are very much focused on CO2. And I think this kind of analysis really shows that animal agriculture really needs to be actually quite central in those CO2 discussions as well. So governments need to include this kind of shift in their revised commitments over the next year that they will be making to the Paris Agreement. And not only that, but these policies really need to be done in a comprehensive way so that we're basically optimizing for climate, ecosystem and human health benefits across the board in one policy. And I was asked how this would sort of, or how it could look among policymakers and corporations and consumers. So I've just put a few ideas. Obviously, we have the NDCs, which could be a central way for policymakers to actually implement these shifts. But we also have a lot of stuff going on at the national level. So we have food health, farming, biodiversity, environmental policies where these shifts could actually come in for implementation. And of course, we have the more obvious things such as shifting subsidies and providing incentives to land users to actually implement these shifts. We have a potential role for corporations in this, which some of you might shudder at and think corporations should have less of a role in the food system, but actually some of the partnerships that we're seeing with farmers to actually assist them to transition their production to either restoring to native vegetation or from shifting feed crops to food crops could actually be really important, especially in those early stages to actually get these shifts moving. The food industry could also increase its availability and accessibility of plant-based options. So instead of making this a sort of high-end, it's only kind of accessible to the high-end on the consumer spectrum, actually just make these options available to everybody. They could also commit to sales targets. I think Tesco might have done this recently, where they actually have a sales target for plant-based products, or alternatively in a sort of dining hall setting, they could actually commit to having a default vegan menu. Consumers, of course, we can all eat more plants. That's an option. We could also request changes in our kind of food environment. So where we eat and shop, we could actually request to see an increase in plant-based offerings. We could contact our political representatives, and we could also contribute to public consultation. So I don't think any of these are really new, but it just kind of demonstrates that there are a lot of different ways that these kind of shifts could happen going forward. And yeah, just to finish with, of course, we all know that this is increasingly an urgent issue. And with those savings that I presented, that was actually a 30-year time frame. So it's really crucial for these kind of shifts to happen sooner rather than later, given that sort of 30-year period to actually achieve those carbon sequestration amounts. And just to finish, the results that the analyses that I presented are available in full. So this is the UK analysis. You can download that full report there. And the global analysis, this is a read version that you can access online as well. And that's it. So thanks so much.